Alright folks, 7-3 is double angle, half angle, product sum formulas, and they can also be some product formulas. I'll also talk about some power reducing formulas. My goal for us is to derive some of these, not all of them, just a handful. Maybe, if you have interest in where like the power reducing ones will show, they're pretty easy. If you have an interest on where like the product of sum or some of the product formulas show up, a quick YouTube search will show you how they're generated. They're not hard algebraically, but usually getting the relationship that you need to start things with is where people kind of get stuck. Once you get the relationship, it's going to drive the actual creation of the formula. The algebra is pretty easy. These are double angle formulas. So what's happening here is, previously we've worked with sine of x or cosine of x or tangent of x. Now the argument has become 2x or 2 theta, depending on what variable they want to choose. What is important to realize, though, is that let's say we're asking what the sine of 60 is. Well, 60 can be rewritten as sine of 2 times 30, where 30 is the x, and then obviously you see the 2 and the 2. So what does that allow me to do? It allows me to find the sine of 60 by knowing just the sine and cosine of 30. Okay, so let's just see if this works. So we already know from the unit circle the sine of 60 degrees. Okay, if we're right there, the sine of 60 degrees, cosine's 1/2, sine is √3/2. So let's see if we get the same thing by knowing just the sine of 30. Remember, the sine of 30 is 1/2. So if we go ahead and say sine of 60 is the same as sine of 2 times 30, then that is equal to 2 times the sine of 30 times the cosine of 30. Well, 2 times the sine of 30 is 1/2. So this sine of 30 becomes 1/2, so 2 times 1/2. And cosine of 30 is √3/2. And if we do that, 2 times 1/2, those are reciprocals, and I'm just left with √3/2. That is exactly what we were looking for. Sine of 60 is √3/2. So this is just a technique that allows us to look at angles like 60 or maybe even 120, find a sine of 120 now knowing the sine of 60, being able to double things, okay? Now, per the unit circle, usually that doesn't give us anything new, because if we go around the unit circle, we got 30, 60, 120, all the way around, because it's generated by multiples of essentially 30 degrees, this doesn't generate any new angles for us, kind of like the sum and difference formulas generate like the 15 degree and 75 degree increments. This doesn't give me anything new. It's just a different way or an alternative way of finding something that we already know to be true. But let's kind of talk about the formula. What's really beneficial here is, like in an equation, if they give me sine of 2x in an equation, that's a pain in the butt. We don't like dealing with that very often. If that's what they start me with, I'm going to probably most of the time substitute that. Okay, and then you see that it makes the argument go to 1x, which is easier to deal with that equations. Let's talk about how this sine of 2x is generated. Okay, we're going to start with the sine of x plus x. Okay, and obviously that is the same as the sine of 2x. That's exactly what we're looking for. And the reason I write it this way, you remember previously, if we had the sine of like an alpha plus a beta, that was sine of alpha cosine of beta, same sign as this, so plus, and then cosine of alpha sine of beta. Okay, so the only thing that is happening here now is that alpha is x and beta is x. So let's see what happens there. We're going to have then sine of x, cosine of x, plus cosine of x, sine of x. Well, commutative property tells us that this thing in the back can be rewritten as sine of x, cosine of x, and now that and that are like terms, so we have two of them. 2 sine of x is cosine of x, and that's where our sine of 2x formula is derived. Okay, cosine formulas are the same way, so let's just do those real quick. Cosine of 2x can be broken down as cosine of x plus x. Now using our sum and difference formula for cosine, remember cosine goes cosine of our angle, first angle, cosine of our second angle, then the opposite sign, and then it goes sine of the angle, first angle, sine of the second angle. Well, if the first angle is x and the second angle is x, it goes like that, and that will give us then that cosine of 2x is equal to cosine squared x minus sine squared x. And then you'll see that there's generally 3 cosine double angle formulas that, or variations of it that we can have, because remember, cosine squared x plus sine squared x equals 1. So if I want to replace that one with, let's say, sine squared, or sorry, not, so I'm going to replace that cosine squared right there with 1 minus sine squared. So I'd have 1 minus sine squared x minus sine squared x. So those two things that I have in boxes, that one and that one, are the same per that identity. So how many sine squares do you have? You're going to have minus 2, so it's 1 minus 2 sine squared x. That is an alternative form of your cosine double angle form. Okay. Well, we can get an alternative form by substituting this one instead. So we'll keep the cosine squared, right there, but now it's going to be minus. Now let's replace sine squared. So sine squared is the same as 1 minus cosine squared. So 1 minus cosine squared. And it's a difference, so I got to subtract a difference here. So it's going to be cosine squared x minus 1 plus cosine squared x. Well, that gives me 2 cosine squared x's minus 1. And those are the quick proofs. Now I know I go through them fast. If you gotta watch them again, slow things down, take detailed notes. But those generate this stuff over here. Okay. Then the tangent formula is generated by taking sine divided by cosine. Okay. And what you're gonna find out is by selectively, and I'll skip this one for now just to save time, selectively choosing, obviously that's got to be your numerator, but then thoughtfully choosing the correct one of these, things are going to cancel out nicely and leave you this formula for tangent of 2x. Okay, so let's come down here and actually talk about what's the purpose of this. So in an equation, and when we get to equations here at the end of chapter 7, you're going to see maybe an argument of 3x in it. We don't generally like that. We want to rewrite it so that it only has 1x. It makes things a little bit easier. So here, this example will be pretty common later on working with equations. The goal is to take cosine of 3x and rewrite it in terms of cosine of x. So this is the technique that we use. So I'll take cosine of 3x, and this works no matter what this is, 3x, 4x, 5x, 6x, but we're going to take and break this apart into cosine of 2x plus x. So now we use our sum and difference formulas for cosine. So that is cosine of 2x, cosine of x, minus sine of 2x, sine of x. Now I'm going to use my sum and difference formula, my double angle formulas. So cosine of 2x, remember that's cosine squared x minus sine squared x times then cosine of x. This becomes 2 sine x cosine x from my double angle formulas above, times then the sine x. Distribute here, so we get cosine cubed x minus sine squared x cosine x minus then 2 sine squared x cosine x. Remember, the goal is to put everything in terms of cosine, so just remember that the sines actually need to go away here. So because of our Pythagorean identity, we know that. So I'm going to make that substitution with all my sine squareds. So I have cosine cubed x minus, now it'd be 1 minus cosine squared x times the cosine x that's already there, minus then 2, now it'd be 1 minus cosine squared x times the cosine x. Just kind of do this in stages so you don't skip any signs. I'm going to distribute that cosine x through here, so it'd be cosine x minus cosine cubed x. I'm going to take that and that, multiply them together, so that's 2 cosine x, and then distribute it. So it'd be minus 2 cosine x, and then plus 2 cosine cubed x. So now you see that everything is in terms of cosine x. I should combine like terms now. So cosine cubed plus cosine cubed plus 2 cosine cubed is 4 cosine cubed minus cosine x minus 2 cosine x, so minus 3 cosine x. And now we see that we have rewritten cosine 3x so that the argument is only now 1x, cosine 1x. So let's see if that happens. So we get that curve there. We'll go cosine 3x. So let's type in 4 cosine of x cubed minus 3 cosine of x. And you see it, they land on top of each other. In an equation, that is difficult. The argument is, it can be messy. This isn't so bad, okay? And what's nice now here is that this is kind of a cubic relationship. If I let cosine of x be like u, you get 4u cubed minus 3u. And we know, if I'm solving equations, we know what to do with 4u cubed minus 3u. We would factor out a u. That gives us then a depreciated quadratic, and we can factor that. So that's kind of where this stuff is going to go. You'll see several questions in your homework that are like this. Like I said, it doesn't matter if it's 3x, 5x. You know, if it's 4x, obviously you go cosine of 4x is equal to cosine 2x plus 2x. Cosine of 5x, you're going to write that as cosine of 2x plus 3x. And you just keep, when you see this, you'll actually have, what happens is, and I don't know which one of these it's going to be, but that might still be a 2x. Then you would go, it just makes you go through this process, one more iteration of substitution, and you'll eventually get down to something that has only arguments of x. These formulas here are what we call power reducing, or it says formulas for lowering powers. Ultimately, if I have something squared, or the third or fourth or whatever it is in my formula or my equation, and I don't want that there, I can reduce the power by putting that in. And this is simply coming from the idea that what we've got, so let's say let's come back up. So the sine and cosine. So the sine, we'll do the sine one. The sine one comes from this right here. So cosine of 2x. So it's one formula, cosine of 2x. So I'll prove this one. The cosine of 2x is equal to 1 minus sine squared, or sorry, 1 minus 2 sine squared x. So that again is this formula right here. Cosine of 2x is equal to 1 minus 2 sine squared x. And now if I just solve for sine squared, so I'll subtract 1, so I get cosine of 2x minus 1 equals negative 2 sine squared x. And now divide by negative 2, so it's going to give me negative cosine 2x plus 1/2. I guess, sorry, did that wrong. It'd be that, and then that is equal to sine squared x. Those are common denominator, so I'm going to rewrite this 1 minus cosine of 2x all over 2 is equal to sine squared x. So there you see, if you start with the sine squared and you want to get rid of the power of 2, you can rewrite it this way. Okay. So here's an example of this. It says express sine squared x cosine squared x in terms of the first power of cosine. So doing that, so sine squared is 1 minus cosine of 2x over 2. And cosine squared x is this one, so 1 plus cosine of 2x over 2. The nice thing about this is that these are actually conjugates. Now when I do this, for this example, so the denominator is going to become 4. Conjugates mean I just multiply the first times first, and now last times last, so getting minus cosine squared of 2x. Okay, so it's better, but it still says that I've got powers of 2. I want first power of cosine, so I got power of 2 here. So what I'm going to do then is rewrite this as 1 minus, now, so cosine squared can be written this way. It's going to be 1 minus, that's going to be the quantity, 1 plus cosine, I'm going to put parentheses right there for a moment. What should go there? Now remember, so if that was x, this is double that. So right now, the way I'm using this is 2x. Okay? So this thing here would be actually 2x. So let's make this double. So that's actually going to be 4x there. So now we can, if you want to, it's not essential, but you can start simplifying this further. For time's sake, I'm going to leave it that way, but I'm going to type it in to see if they match up. So let's see here. So cosine squared and sine squared. So sine squared x times cosine squared x. Gives me that graph there, and everything's squared, so that makes sense that it's all above the x-axis here. It's all positive. So now I'm going to type in 1 minus the quantity, 1 plus cosine of 4x. Okay, I want all of that over 2, and then all of that. Okay, you can kind of see the purple, or not the purple, the orange one is almost like this blue one. It's just taller. So how much taller is it? It's 4 times as tall. So if I divide by 4, we get the same image. But what's the benefit of this? Now we no longer have powers of 2. It's all in powers of 1. We could, if it called for it, if we were needed to, we could now depreciate this 4x, because obviously it's a 2x plus 2x there. We use our double angle formulas to get that all down to the cosine of 1x. This question's not asking for that. You won't see anything, I don't think, in that regard. All right. So the next formulas are what we call half angle formulas. Okay. So this is the idea that if I know, basically this is the idea, if you know sine of 60, then using the half angle formulas, you should know sine of 30 instantly, okay? Or through the use of these. I don't want to say it's going to be instantaneous, but you should know them. What is real nice is, and this is the new one that shows up on the unit circle, if I know the sine of 45, if I take half of that, I should now know the sine of 22.5. So we do the same thing with cosine as well. So it allows us to find half of angles that we know in the unit circle. These, again, they're not hard to derive. They come from the double angle formulas, actually, the sine one. So let's say that sine of 2x, that was equal to 2 sine x cosine x. Okay. Actually, nope. Using the wrong one. They all come from the cosine double angle formula. So let's go. So cosine of, let's say, 2x, that was equivalent to, it was 1 minus 2 sine squared x was one of them. And then cosine of 2x was equal to another one was 2 cosine squared x minus 1. All right, so we have those two versions of the cosine double angle. And these are where the cosine half angle and the sine half angle show up. And this is all you have to do. You say let 2x equal u. So then x would equal u over 2. And I'm going to make those substitutions now. So I go cosine 2x, I just said let that be u. 1 minus 2 sine squared, this is x, which we said now is that u over 2. So now you see there's a relationship that this is half of whatever that was. So now I'm going to solve for sine of u over 2. So I'm going to go cosine of u minus 1 equals negative 2 sine squared of u over 2. Divide both sides by negative 2. So I'm going to do this. It's going to turn this into a positive, so it'll be 1. Turn that into a negative, so it's going to be cosine of u. It'll all be over 2. That is then equal to sine squared of u over 2. So I'm going to square root now. We get 1 minus cosine of u over 2. Plus or minus. And then equal to sine of u over 2. Okay. The only thing that here, the plus or minus depends on the quadrant in which u over 2 lies. Okay. So something to think about in choosing the plus or minus. If I just write this in terms of, let's say, u, so let's go 0, there's 90, there's 180, and 270, and then 360. So if my original angle is somewhere between 0 and 90, then u over 2 is going to be in the first quadrant. If my angle is somewhere between 180 and 90, u over 2, okay, think about like taking 160. 160 divided by 2 is 80, okay? So if I've got an angle over here and I take half of it, it's going to put me somewhere over here. Okay, so let's say, so 90, I think about like 91 divided by 2. That's going to put me at 45.5. So it put me like right there. If I take 180 divided by 2, it's going to put me at 90 right there. Okay, so if they give me an angle that's between 90 and 180, this is where the half angle is going to show up. We're going to do the same thing down here. Basically, so the idea is if they give me an angle between 180 and 270, then the half angle is going to be between 90 and 135. Take half of that, take half of that. Same thing over here. Be between 135 and 180. So that's how we then choose whether we use the plus or minus. The cosine then, half angle, is generated from taking that one, doing the same substitutions of 2x equals u and x equals u over 2, solving then for cosine of u over 2, and you'll generate this. Then if I divide those, take that divided by that, okay, things will cancel out nicely and give you this, okay. which is ultimately, after multiplying by the conjugate of this, will actually generate that formula. So these are all variations of the tangent half angle formula. Alright, so how do we use this? It says find the exact value of sine of 22.5. So sine of 22.5, what we need to understand is that this is the same thing as sine of 45 over 2. The 45 then is now my u for my formula. So I'm going to go plus or minus. It's now 1 minus cosine of u, which is 45, all over 2. So now it's going to be plus or minus 1 minus square root of 2 over 2, all over 2. We can go ahead and simplify this, so it's going to be, the top is, so I'm going to write that as 2 over 2, so it would be 2 minus root 2 over 2, all over 2 over 1, multiplied by that reciprocal, so it would be 1/2. So now I'm going to get the square root of 2 minus root 2 over 4. I can, and I'm running out of room here, rewrite this as the root 2 minus root 2 all over 2. That 4 can come out. And now it's still plus or minus. But remember, when we choose that, remember u was 45 degrees, so u is right there. Well, if I take, so the sign there is positive. If I take half of that, u over 2 is going to be right there. The sign is still going to be positive. So that's the y value that I'm choosing. So it'll be positive. Okay. So let's grab, use Desmos here. Okay, so all I've done is, here in Desmos, just went ahead and typed in sine 22.5, typed in exactly what I came up with as the radical. That's the exact value. You see that the decimal versions are the same. So what does this tell me? That's telling us that when we look at the unit circle, and I'm looking at 22.5 degrees, the y value as an exact value is that right there. Okay. You can't simplify a nested radical like this. Okay, so we just leave it as radical 2 minus root 2 as I've got it written here. Alright, going on to the next style of question. Okay, it says evaluate the sine of 2 theta where cosine is equal to negative 2/5. Theta is in quadrant 2. Okay, so theta is in quadrant 2. So let's just think about this real quick. If theta is in quadrant 2, which is 90 to 180, then 2 theta, multiply that by 2, multiply that by 2, okay, is going to put me, that's going to go to 180, and this is going to go to 360. So right now it's going to tell me that essentially 2 theta is in either quadrant 3 or quadrant 4, and we'll just talk about how we kind of narrow that down here in a little bit. But if I'm looking for the sine, does it really matter? If I'm going to be in the 3rd quadrant or the 4th quadrant, the sine is negative in both. So that's something to think about as we work through this. This is another one of those questions where we've got to draw a picture. Okay, so they're giving us the sine of 2 theta is what we're being asked for, and we're trying to evaluate that. Well, I don't even know what theta is, so what we're going to try to do is we're going to try to rewrite this. So sine 2 theta using my double angle formula is this. And the reason we're using my double angle formula is because right here it tells me what cosine of theta is. It tells me exactly what that is right there. But I don't know what this is. But if I draw a picture, the cosine of theta, theta in quadrant 2, looks like this. Negative 2, that's 5. Okay, so how do I find this vertical distance here? I use the Pythagorean theorem. Okay, so I'll say 25 minus 4 gives me 21. So this is root 21. Okay, so remember that's theta. So sine of theta would be radical 21 over 5. Cosine is negative 2/5. So now I get negative 4 radical 21 all over 25. And that's what we're looking for then. And just think, is that if theta was in quadrant 2, 2 theta's either got to be in quadrant 3 or 4. And in the third, fourth quadrant, isn't the sine value negative? Now we can check this. It's a little bit of a messy check. First thing we're going to do to check this is figure out what angle cosine of theta is talking about when it says negative 2/5. So I'm going to figure out what that theta is. So we're going to go arc cosine of negative 2/5. So 113 degrees is the theta that we're describing here. Okay, so I'm just going to call that T for theta. Alright, then sine of 2 theta should give me that there. I just want to make sure I'm in degrees. Yeah, okay. So then we should then realize that negative 4 times the square root of 21 all divided by 25 should give us the same exact thing. Okay. A lot of questions that, and you've seen us do this kind of the same thing in the past. When we don't initially know what theta is and they ask us to find 2 theta, we can do that. But the check then is actually use the cosine inverse in this case to find out what theta is. Then find out sine of 2 theta. And when that gives you a decimal approximation, does that match to that? Excuse me. Alright, so we've got some formulas down here. I'm not going to prove them. We're running kind of late on this, or long, I guess, on this video already. These are our product to sum and our sum to product formulas. And essentially what you see here is that you start with a product of cosine of u and v. Okay, so sine of u, cosine of v. So the idea here is that u is a different argument than v. So this might be like sine of, if we're using specific values, maybe sine of 30 times cosine of 60. Well, we can then break it apart this way and see that it gives me the same results this way. But this might be like sine of x and cosine of 2x, or whatever. Okay, so these are very, I think they're hard to remember. They're very similar. If you were to get on my website and look at chapter 7 section 3, you'll find the proofs to these. You might have to scrub through a couple of videos, but they are there. Kind of show you how to use these. This is mainly where we would see them, is in a verifying an identity, or a proof. Basically what they want us to argue is that this thing here, which is nasty looking, is exactly the same thing as tangent. So you remember the way we've done some of these in the past, specifically in section 7.2, we would say the left hand side is equal to sine of 3x minus sine of x over cosine of 3x plus cosine of x. And right now you can see that would be like your u, and that would be the v that you're seeing previously when it was written as product to sum. I guess here they're using x's and y's the way in the textbook that I cut these out of. So that's x and that's y. So we can actually see that we're taking the sine of some argument minus the sine of a different argument. So we're using that rule right there. So I'm going to rewrite this now as the numerator is 2 cosine. So now we see that it's x plus y. So now you're going to add those together. So it's 3x plus x. So 4x over 2. Over that 2 right there. So when I do that, obviously I think I can rewrite that. We can all agree that 4x over 2 is the same as 2x. And then this is going to be sine of x minus y. So 3x minus x. So it'd be 2x over 2. Which again, I think we can all agree that that's just x. So that's nice. Now the bottom is the cosine. And it's a sum, so I'm just trying to figure out, what does that one look like? It looks just like that right there, with the x's and y's are 3x and x respectively. So then it's going to turn into 2 cosine, add your x and your y together, so add your two arguments together, that gives you 4x, so that'd be that there, divided by 2 gives you 2x. And then we're going to go cosine, subtract your x and y, so subtract 3x and x gives you 2x, divide that by 2, and it gives you x. Well, what do you notice about that right there? Gives you 1. They cancel out. So then you're left with just sine x over cosine x, which then is obviously tangent x. Which is then obviously our right-hand side. So that's kind of how we would finish it. A lot of times with these proofs, you'll see this little square with it's shaded in. They call it, I forget the guy's name, I think it starts with an H, but they call it whatever his name is, Tombstone. Just finalizing that we are done. You might see sometimes like this, which is, I forget what the phrase again is, but it's Latin for something, but translated simply means we have proven what we set out to prove. Alright, so I'm just going to zip through the rest of these examples. Example 6 says sine of 1/2 equals cosine inverse of x. Okay, so this is a composite function. We're going to see what cosine inverse of x is. So remember what cosine inverse of x does. Whenever we see a cosine inverse, sine inverse, tangent inverse, we're going to draw a picture. Cosine inverse, we're going to assume it's in the first quadrant here. Okay, we can get numbers from 0 to 180 back. But if I do that, so that would be x and that would be 1, because this is, remember, what goes in there is the ratio of the adjacent side divided by the hypotenuse. That means that this distance here is 1 minus x squared underneath the square root. Just found that using Pythagorean theorem. So that gives me this theta there. So what are they doing here? They're saying sine of 1/2, and now this thing created that theta. So theta. So cosine inverse of a ratio, remember, splits back an angle. The angle splits back as theta. So right now we've got the sine of theta over 2. Well, that's a half angle. Half angle, okay? And because we're in the first quadrant here, we're going to have a y value that's positive here. Remember, it's 1. Okay, sine is, I believe it's 1 minus cosine. I get them confused a little bit. Yeah, 1 minus cosine of u over 2. Back to it. 1 minus cosine okay, so because I'm using, this is theta over 2, and this is just theta, and then over 2. Okay? So now I look at this and say, well, what was the cosine of theta? Well, it was, remember, cosine is adjacent divided by hypotenuse, so it's just x. So I'm going to say this is 1 minus x all over 2. And we should now you see here what we've done is we've taken something that was trigonometric and we've rewritten so it is purely algebraic. And let's just see if they give us the same thing. So I'm going to sine of 1/2, so I should put 0.5, and then arc cosine of x, and we get that curve there. So now I'm just going to type in what we thought it was algebraically, which was the square root of 1 minus x. Okay, so that's kind of looking what we want. But remember, we got to put that over 2. And we get that. Now, the only thing is that we've got to pay attention to is this idea here. Remember the cosine inverse. The cosine inverse is only identified for values between -1 and 1. So that's why this thing here obviously goes on much more to the left or further to the left. It goes on negative infinity essentially. So we just have to restrict that and say, well, because this cosine inverse, that ratio right there can only be between -1 and 1, then this thing here, when I graph that, I really don't want to graph that between -1 and 1 for the same reason. This next one. So again, sine inverse of x is going to give me, so sine is that. So then this here would be 1 minus x squared underneath the radical, and that gives us theta. So it gives us that theta. So now I'm looking at cosine of now 2 theta. Because that's what this turns into. Sine inverse of x gives me that theta. So now I just got to figure out which one do I want to use. Do I want to use cosine squared x minus sine squared x? Do I want to use 1 minus 2 sine squared x? Or do I want to use 2 cosine squared x minus 1? It doesn't matter. Each one of these is fine. They're going to give you the same thing. I'm going to use, just because the algebra is going to be easier, I'm going to use the one that uses that stuff, so the sine of x. So I'm going to use that one. So we're going to go cosine of 2 theta here is, and I should be using thetas in here instead of x's, doesn't matter. 1 minus 2 sine squared theta. So let's look at our picture. We got 1 minus 2. Now, theta is going to be x, or sorry, sine of theta is x over 1. So if I square that, I should get that. So let's just check to see. So this is, obviously, this is a parabola. Concave down. Shifted up 1 unit. Let's go ahead and graph that 1 minus 2x squared. Okay. Now let's just think about, because of the sine function, the sine inverse, only being defined between -1 and 1. Let's kind of see what happens here when we graph the cosine of 2 arc sine of x, which is what we started with. You see that green curve is only between -1 and 1 because of that restriction. That input has to be a number between -1 and 1 to get an angle back. So because that is only defined from -1, so I can only get a number back inside these parentheses here if that number right there is between -1 and 1. So that's why this image is restricted there. So when I'm done and I get this here algebraically, I would have to say, except for I need to keep the domain between -1 and 1. So I'd write comma, -1 is less than or equal to x is less than or equal to 1, so that I do restrict it correctly. But that's just a quick check out, or graphically, to see that we have indeed come up with the correct version algebraically of this trigonometric expression. This next one, write the product as a sum. So product as a sum. So it's so you just got to match the format here. It's cosine cosine. So cosine u, cosine v. So cosine cosine. So it's this one right here. So I'm just going to actually copy that. We'll pull it down here. Just see a couple of these in your homework. And if you can think about it, so this here, this would be my u, and that would be my v that is showing up in the formula. So I'm going to go 1/2. It'll be cosine of now 8x. So you add the u and the v, so add 5x and 3x. Plus then cosine of, you subtract them, and it'll be 2x. So I get cosine of 8x plus cosine of 2x all over 2. That's all you're looking for there. If they could make this much more difficult and say that you can only have it with arguments of 1x or something like that. So then you would use your double angle formulas to break these all the way down. Not really going to ask you to do too much of that. This one is write the sum as a product. So now we'll go match the one that says cosine u plus cosine v. Cosine u plus cosine v. Or I guess in this case I was using x's and y's. So we're going to grab this one here. Come back down here, just match. And I'll give these to you on tests and quizzes. These are nasty to remember. But now you see that this x here is really that 11x, and this y is that 8x. So we'll go 2 cosine. This is asking us to add them together, so you get 19x over 2. And then cosine of, this is you subtracting them, so it's going to give you 3x over 2. The one nice thing, again, all of this stuff, and this is the whole course, you can check this, you can check it graphically, is the cosine of 11x plus cosine of 8x. Okay, if I look at that graph, it's really kind of a boring looking graph, not much going on there. But is that the same thing then as 2 cosine of 19x over 2 cosine of 3x over 2. And you can see then that the red and blue graphs indeed overlap each other. So we got two equal versions of the same thing. I like these questions because they make you draw pictures. You'll definitely see one of these on your tests for this chapter. So let's find sine of 2x, cosine 2x, tangent 2x, knowing this information. Okay, so knowing that information, remember tangent. Okay, all students take calculus. So tangent is going to be negative in the second and the fourth quadrants. Okay, this is saying that cosine is positive. Well, cosine is only positive in that quadrant and that quadrant. So with all the information going on here, I know I should be the angle x that they're talking about is between 270 degrees and 360 degrees. That's the idea that's happening here. Okay. That being said, then when I find the double angle, okay, so this is a positive negative for an angle, okay, for anything that's showing up in the fourth quadrant, any point in there is positive negative. If I double this, that becomes 720, and this becomes 540. Okay, so that's kind of what we're thinking about here in terms of choosing the correct sign of sine 2x, cosine 2x, tangent 2x. If it comes down to it, it'll be something out of the fourth quadrant. Okay, so sine of 2x. First thing I have to do is realize that sine of 2x is equal to 2 sine of x cosine of x. The problem, I don't know any of that stuff. All I know is that. Okay? But I do know that we're in the fourth quadrant. Tangent. Okay, so basically here we're telling us that this is x. Tangent is the opposite over adjacent. And in this case, I know that that's got to be negative because that's in the fourth quadrant. So now Pythagorean theorem says 6 squared plus 1 squared. Now take square root, it should give me that there. So now we should know that the sine of 2x is equal to 2 sine of x cosine of x. But let's look at sine of x real quick. Right here, sine of x would be negative 1 over root 37. cosine would be 6 over root 37. This is going to be negative 12 over root 37 as my final answer. Now, how can I guarantee to see if that is accurate? We again come to this. Okay. I said tangent, so arctangent of negative 1/6 gave me that angle right there. Just make sure I'm in radians, or sorry, degrees. I want to be in degrees. Make sure I'm not in radians. Okay. So it gives me that. So I don't. Obviously, that's a fourth quadrant angle. So I'm going to actually take 360 plus that. That's the angle I'm actually talking about. 350.53. So if I go, so let's call that T. Okay, so then the sine of 2t should be that number right there. Well, is that negative 12 divided by the square root of 37? And it's not. So what do we do here? T square that, add them together. So 36, 1, 37, square root 37. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Multiply those together. So negative. Alright, see what I did. We multiply these here together. Square root times square root obviously gets that thing to go away. So it should be that, and then getting rid of that over here. Now you see they're the same. Okay, so negative 12/37 is what we're looking for, sine of 2x. So cosine of 2x then, let's do the same thing. Just do it right here. Cosine of 2x. I'm going to go 1 minus 2 sine squared x. You can use any one of the formulas. I like using that one. So 1 minus 2. Okay, now sine of x, again using the same picture, sine is negative 1 over root 37. And we'll square that. Okay, so it gives me 1 over 37. So it's going to be 1 minus 2 over 37. So if we go, what's that, 37 over 37, so what's it, 35 over 37. So 35 37ths should be positive because it's in the fourth quadrant. Cosine in the fourth quadrant is positive. Now if I go cosine of, remember t, the angle that we were actually looking at was 350, so we go twice that, you see that those two numbers are then the same. Okay. Now this is the reason, this is the main reason I don't often use the tangent double angle formula. You could, but I'm not going to, because I know the tangent of 2x is the same thing as sine of 2x divided by cosine of 2x. And we just found sine of 2x was negative 12 over 37. Cosine of 2x was 35 over 37. So that tells me the tangent of 2x is negative 12 over 35. Just double check. Take negative 12 divided by 35, gives you that number there. And then tangent of 2t, we see it's the same number. Alright, so that's how you do double angles, and you see a couple examples like that in your homework. Here, obviously, I use the sine. You could have gone 2 cosine squared x minus 1 as your formula here, and you would have still found 35 37ths. Or you could use cosine squared minus sine squared and still found 35 37ths. Down here, I'll just do sine of x over 2. Remember, that is plus or minus. So it'll be 1 minus cosine of, in this case, x over 2. Okay, if you come back up here, where'd they go? We're looking at these guys. So sine is the one that's minus, cosine would be the one that has the plus sign here. Alright, so the interesting thing here is they tell you that your original angle, your full angle, is between 0 and 90, so then your half angle, when we're done, your half angle is going to be between 0 and 45. Okay? If they would have told you that your angle is between, let's actually do it this way. Let's say instead of between 0 and 90, let's just wipe that away. Let's do that. Let's say that that x is between 180 and 90. Okay, now it's not, maybe we don't usually think about it, or inequality that way. We think about it as 90. Think about it that way. So if that's the case, then if I put it over 2, like this, then that means 45, my half angle is between 45 and 90. So it should be put in the first quadrant. And that's something to think about because it tells me how to choose that plus or minus appropriately. But again, drawing the picture, because if I'm going to find the sine, I need to know what the cosine is. So my picture is what's going to allow me to do that. Now tell me where we set our angles between 90 and 180. So it's going to be over here in that quadrant. The sine is 24, so 24, that's 25. That's a Pythagorean triple. If you take 25 squared, so 625 minus 24 squared, which is what, 576. You get 49, and that is 7. So this is 7. And the only thing that we got to pay attention to is that it's in the second quadrant, so it's a negative 7. So remember, that's x then. That gives us that angle. Okay? So then, the sine of x over 2 is going to be 1 minus cosine of x. Well, cosine of x, that thing replaces with negative 7/25. It's minus negative 7/25 all over 2. So that's 1, so that's like 25/25. So it's 32/25. 32/25 all over 2. So is it 32/50? So root 32/50. When we simplify that now, because I know I need to be, my half angle is between 45 and 90, then it's a positive root 32/50. Again, you can check that. So let's do it. Now the only thing is we don't know what our original theta was, but we do know that sine of x equals 24/25. So arc sine of 24/25 gives me that measurement there. Put it in degrees, so 73 degrees. But remember, this says that we were in the second quadrant. Okay, so I've actually got to take 180 minus that, and that is actually the theta, or in this case, I guess we're using x, but that is the complete angle. Okay, so then if I want to find sine of the half angle, it would be t divided by 2, which turns out to be that number right there, which if we go square root of 32/50, you see that it gives me ultimately that, so that'll reduce to 4/5. That's a fraction that did not reduce, or a root that did not reduce. But we see then that knowing what the angle is, then I can guarantee that this is the exact version of it. We can do cosine. So cosine, it's really nothing different. Cosine of x over 2 is equal to, now that formula is plus or minus, it's 1 plus cosine of x over 2 So now I look at 1 plus cosine of x. So cosine of x over here would have been -7/25 all over 2. So again, that's 25/25. So it's like it'll be 18/25 over 2. So it turns out to be 18/50. So now I can go say, okay, well, what's the square root of 18/50? Gives me 0.6. Is that the same thing as the cosine of t over 2? And it is. So now, if I want to find out what the tangent is, I'm just going to divide that by that. Or sine. So tangent of my half angle should equal the sine of my half angle divided by the cosine of my half angle. So that's, what is it, 0.8 divided by 0.6. Okay. And when we do that, 0.8 divided by 0.6 gives me that number there. And then let's go tangent of t over 2. And we see that it's still 1.3333. Alright, so I know that's quite a few examples. And I know it's a lengthy video. But it's essential for our understanding of this stuff for the next couple sections that are going to involve working with equations. To be blatantly honest with you, now I'll give you some practice problems that involve all these things, but your number one formulas that you're going to be kind of fixated on for the rest of the course and what you use in calculus, for the most part, are your double angle formulas. Okay. And when I learned those, and here's the thing, before today I didn't know them off the top of my head, okay? But I know where they come from. I know they come from my sum and difference formulas. But if you know those two, the other ones, these specifically, can be found just doing a little bit of quick algebra with these two. You're not going to use these a whole lot. Okay, these power reducing formulas, these are essential. These become very useful in working with integrals in calculus. So those become very important formulas. Again, I don't know what that one is. You ask me tomorrow what that one is, I don't know. But I'll know what these two are, and I'll take those two and divide them to get that one. So use those quite a bit. You rarely see these two in application. So double angles, half angles, those are the ones that we want to really focus on, because they become, like I said, essential in other sections, other courses.